Hello class! Today we are going to talk about similar polygons. Now this should all be reviewed. You should have all learned this back in junior high, but that was years ago and you may have forgotten some of that. That's okay. So we're going to go over it again. Similar polygons, if you remember, when you first learned about this, you learned similar shapes were the same shape but different size, right? Okay, we're going to get a little bit more technical in here. The way this is defining it is something that is made using a similarity transformation, which we talked about earlier. These are things with a dilation involved. Might have a rotation or reflection there, but it's got to have that dilation, which changes the size, doesn't change shape. All right. And what we're going to do, we are going to use a similarity statement to do this. And that's better. All right. This is a similarity statement. Just like we had congruent statements that said triangle ABC is congruent to triangle DEF, we have similarity statements. Triangle ABC is similar. This little squiggle right here, that means similar to triangle DEF. All right. And when you do this, we change it from triangle ABC to triangle DEF. If you'll notice, the angles all stay the same. Okay, so the corresponding angles will be congruent, because if the angles change, we've got a different shape. It's not the same shape if it's got different angles. All right. However, the sides do not stay the same. Okay, the sides are all going to be enlarged or reduced by a scale factor, k, which means the sides are proportional. You may remember that. The sides are proportional. We do that cross, multiply, and divide to figure out the missing side, right? You may or may not have done it in junior high using scale factor. All right. So the things to remember, the corresponding angles will be congruent. And in your similarity statement, they need to stay in the same order just like they were in the congruent statement. So ABC, A corresponds to D, B corresponds to E, C corresponds to F. So those angles are still going to be congruent, just like in the congruent statement we had earlier. All right. Now, the sides are not congruent. The sides are going to be proportional. And if you remember, that proportion is going to be new over old. All right. The new stuff, segment DE, over the original segment AB. New over old. Okay? And that is going to be the same. DE over AB is going to be the same as EF over BC, which is the same thing as FD over CA. And whatever that ratio is, that is the scale factor, which is K. All right? Okay, so let's take a look at some different properties, other things here. First off, in a similar polygon, all of the corresponding lengths are going to be proportional. They are all going to have that same scale factor. That means we're not just talking about the lengths of the sides, we're also talking about the height, we're talking about the width, we're talking about the length of the base, we're talking about the altitude, which is the same as height, but we're talking about medians, mid-segments, everything. It is all going to be proportional. Doesn't matter if it's the side. It's all proportional if the triangles are similar. Okay? So that is very useful, and that's very good to know. All right. Next, we're going to look at perimeter. We have a theorem for this, perimeter of similar polygons. So if you got two similar polygons, the ratio between the perimeters is going to equal the ratio between the corresponding sides. So if KLMN is similar to PQRS, then the perimeter, add up all the sides over the original perimeter, is going to equal the ratio between the sides, which is that scale factor that we had up here. Okay? So the perimeter is proportional. Same proportion as the sides. It's going to have the same scale factor. And so we can do the same thing. We can cross, multiply, and divide. You can do it that way, or cross products, however you do proportions. Areas, on the other hand, are not. Areas are, the ratio between the areas is going to be equal to the squares of the ratio between the corresponding sides. Okay, so the area of PQRS over the area of KLMN is going to equal that ratio, same ratio we had here, that was scale factor. It's going to equal that scale factor squared. All right, So perimeters, we can just multiply by the scale factor and everything's good. Area, we do not multiply by the scale factor. Area, we multiply the scale factor squared. And the reason for that is because you have multiplied one side, you've multiplied the other side, and then for area, you take the two dimensions and you multiply the two dimensions together. So I've multiplied here by k, I've multiplied that by k, and then I'm going to multiply those two k's together, which gives me k squared. This one, I'm multiplying them all by k, yes, but then basically I'm just distributing it. Right? It's k times this, k times that, k times that, k times that, and you add it all up, which is the same as adding them all up and multiplying by k. It's just distribution. Right? Okay, so that is all of the informational stuff. Let's get into some application. Let's do some problems with this. Okay, so exercise 1 and 2, the polygons are similar, which is good. That means we can do this using proportions. We need the value of x. Now, the first one, this is real easy. This is a nice little junior high problem. And we need to find x. So that's not hard. We're going to set up our ratios, right? We'll call this the new one and that the old one. So it'll be 3 over 2, short side over short side. Those correspond. And then long side over long side. So 7 over x. Those are corresponding. And now we've got a proportion. We can solve this nice and easy. We have cross products. So 3x equals 2 times 7, right? So 3x equals 14. Divide both sides by 3. And we have x equals, well, that doesn't divide neatly, so we just leave it as a fraction because fractions are your friend. 14 thirds. Now, if you want, we could change this into a mixed number, in which case that would be what? 4 and 2 thirds. If you want to change it into a decimal, don't. All right? Thirds are a repeating decimal. They go on forever, and we don't like rounding. So we're just going to leave this as 4 and 2 thirds. Well, 14 thirds. 14 thirds is fine, too. I like 14 thirds. All right? But you don't want to call this 4.6 because it is not 4.6. If you want to change it to decimal, it would be 4.6 with a little bar above it, repeating 6. That would be okay, but fractions are preferred because they're not rounded off. It's more exact. All right, so I would like everybody to pause the video and find x in problem 2. All right, let's see how you did. Here we go. We have x is over here on the little side, and this is between the angle that has 1 course and the one that has 3. So 1 and 3, it's going to correspond with the 25. So we'll say x is the new one, and 25 is the old one, so x over 25. And which one are we going to use to finish up our proportion? Doesn't matter. Use whichever one you like. I think I will use the 12 and the 20. Why not? Okay, so I said this is my new one, so new over old. No, not 12 and 20. 12 doesn't go with 20, does it? Okay, well, let's take a look. So 12 is going to go with 30 because it's 2 and 3. 2 and 3 tick marks, so 12 goes with 30. All right, so this is kind of big, but that's okay. So we have 30x equals 25 times 12. 30x, not 3x, 30x. And let's see, 25, so this is 12 quarters, so this is $3. 300. There we go. And now we divide both sides by 30. Divide by 30, because we want to get x by itself, and x equals 10. There it is. Nice and easy. Easy peasy. Alright, so hopefully y'all are remembering this. Y'all did this ages ago, back when y'all were little. Alright, let's take a look at some things that are slightly more complicated. Not much, because this whole thing is review, so this should all be pretty easy. Okay, so for 3 through 8, we're going to be using figure ABCDE, which is similar to KLM and P. And it tells us, with the little squiggle there, that these are similar to each other. So first, we need to find the scale factor of ABCDE to KLM and P, which means we're going to start here and go to there. So this is old, and this one is new. All right? And the scale factor, remember, is old over new. And it doesn't matter which sides we use as long as we have some corresponding sides. So let's see, we have 2 and 3, that'll work. 1 and, we don't know what x is, 1, we don't know what x is. 2 and 3, that's the same thing, we have 2 and 3. And 3 and 2, square root of 2, and we don't know what that is. So yeah, we're going to use 2 and 3. So let's see, the new is k element p, so it's new 3 over old 2. And that's it. We could simplify it. This is the scale factor. If you really have to have it as a decimal, that's fine. That's 1.5. All right. And this is a decimal, it's okay because it's nice, it stops. It's a terminating decimal, not repeating. So, okay, don't have to round it. Okay, now we want the scale factor from k element p to a, b, c, d, e. So in this time, this is the old and this is the new. Which means instead of going from 2 to 3, we are now going from 3 to 2. So that's 2 over 3, new over old. All right, and so now we have that. And 2/3, I'm not going to change into a decimal because it goes on forever. So we just leave it as 2/3. All right, and that's it. Easy stuff. Now let's see. We need to find the value of x, y, and z. Okay, we'll just start with x. Where's that? So there's x right there. And x corresponds to this one here, because LM is going to correspond to BC. And we can go either way with this, but it's easier to go with what you started with. So we're starting with this one. So this is my old one, and we're going to the new. So we're going to use our scale factor of 3/2. So what we have here, we have 1 times my scale factor, 3/2, which equals, well, 3/2. I'm just multiplying by 1. So 3/2, and that is x. There it is. Not bad. Now we need y. Y is right there. It corresponds with this diagonal thing here. And so that's 3 square roots of 2. 3 square roots of 2 times my scale factor, because I'm going from a, b, c, d, e to k element p. So that is 3/2, which equals, we multiply by fractions, multiply straight across, and we have 9 square roots of 2 over 2, which is kind of hideous. Let's go ahead and change that to a decimal. Let's see what we get here. Turn this on. So we have 9 square roots of 2 divided by 2. Isn't that lovely? 6.36 approximately. Approximately 6.36 for y. So that's approximately the value for y. And depending on who your professor is, depends on whether they would prefer this one or that one. All right. Next we need z. So z is here. This angle here, so it's there. So we need to multiply this one by our scale factor. No, we don't. No, we don't. Because it's angles, remember? That's right. Angles, corresponding angles are congruent to each other. We don't need to mess with any scale factors here because the shape is the same, so the angles are going to be the same. And so we have to do nothing at all for z except for write down that z is the same as that one right there, which is 45. And that's all it takes for z. So angles are nice and easy. So we like those. All right. Now, what we need to do next is to find the perimeter of each polygon. All right. So to find the perimeter of each polygon, we're just going to add up the sides. That's all we're going to do. Just add them up. So we'll start with A, B, C, D, E. A, B, C, D, E. And we have 2 plus 1 plus 1 plus 2 plus 3 square roots of 2, which we're going to go ahead and get this as an actual decimal answer. It's going to be approximate. It won't be the exact answer, but that's okay. It'll get us close. All right, so let's clear that up. We have 2 plus 1 plus 1 plus 2 plus 3 square roots of 2, which is approximately 10.24. 10.24. And now the perimeter of the other polygon, polygon KLMNP, which is 3 plus what was x? X was 3 halves. Plus 3 halves. Plus, I'm going to write it down like that. That way I don't have to round it. 9 squares of 2 over 2. And my answer will be rounded. I'm going to type it in exactly the way it is there. 2 plus 3 halves plus 3 halves plus 3. Whoa, not 2, 3. 3. Plus, and I'll grab that. So 9 square roots of 2 over 2. That way I don't round before I get my answer. I can just round my answer. 15.36. So this is approximately 15.36. Okay, now, next question. Find the ratio of the perimeters of the two figures. Okay, so from A, B, C, D, E to K, L, M, and P. So this is the new one. Sorry, this is the old one. And this is the new one. So we'll have this one over that one. So that would be 15.36 approximately over 10.24. Now I am going to get exact answers because I'm going to use my calculator and just pull those off. So new over old. And I get 1.5. So that's going to be 1.5, which, since we had scale factor before as a fraction, we're going to put this one as a fraction too, and that is 3 halves. You'll notice it is the same thing we had up here. We went from A, B, C, D, E to K, L, M, and P, right? 3 halves or 1.5. 3 halves or 1.5. Right? It's the same thing, just like our lovely little theorems that said it would be. You're going to have the same scale factor. So that's good. We know it works. Number 8, last one. Find the ratio of the areas of figure A, B, C, D, E to K, L, M, and P. So this is going to be old. This is going to be new. Now, to do this, we need to get the areas, right? And these are some nice funky shapes. So we're going to do some little bit of finagling. I'm going to pretend that this is a right triangle, and then I will subtract out that square from the right triangle. That'll make it a little bit easier. Area of a triangle is 1/2 base, which when I add that in, that'll be 3, times height, which if I add that in all the way down, that'll be 3. So that's 1/2 of 3 times 3, and then I am going to subtract out the 1 times 1 for this square, so minus 1 squared. Alright, so let's put that in. We could probably do this in our head, but that's okay. So 1/2 times 3 minus 1 squared, which is 3.5. 3.5. This is for A, B, C, D, E. A, B, C, D, E. Okay, now let's do the other one. K, L, M, and P. We have 1/2 times, let's see, 3 plus, what was this one? This is 3 halves or 1.5, so that's going to be that 4.5 times 4.5 minus this 1.5 squared. Alright, let's see what we get there. Okay, so 0.5 times 4.5 times 4.5 minus 1.5 squared, which is 7.875. 7.875, and this is going to be K, L, M, N, P. Now let's put them in our ratio. New, 7.875 over old, which is 3.5, and let's see what we get. So, new over old, there's my old, and we get 2 1/4. 2 1/4, and just so this is in a fraction, just like everything, all our other ones, let's see here, math frac, 9/4. 9/4. Okay, so there's my answer here, here's my answer there, and if you will notice, this was 3/2. My ratio for the areas is 9/4. So this is 3 squared over 2 squared. This is 3/2 squared, which, if we remember from our theorem back here, it told us that's what it was going to be. Told us it was going to be a scale factor squared. So really we could have just done without all of this and just said, hey, it's going to be 3/2 squared. But that's okay. Always good to test it and prove that the theorems really do work, right? And so there it is. So, in review, similar figures, same shape, different size. So the corresponding angles will be congruent, the corresponding sides will be proportional, and the scale factor for that is going to be new over old. Scale factor works for every length of the figure. It doesn't matter if you're talking about sides, or it doesn't matter if you're talking about altitudes, or mid-segments, or medians. It's all good. All works for the scale factor, even the perimeter, because perimeter is still just length, and it works for all of the lengths. Perimeter is a length, so the scale factor works. Area, however, is not a length, and so the area does not use the scale factor. It uses the scale factor squared because we are getting square units. All right? And I hope you found that useful, and I will see you in the next video.